So, how can we understand the sun? What is going on in its deepest levels? Our desire is to study the sun, but we can't just peer directly into it because apart from being able to see into the photosphere, the sun is opaque from the core out to the photosphere. So we can't just look at it and see the processes going on. We don't have that wonderful opportunity. Mathematical models are very useful for giving us a lot of specificity by understanding the basic gas laws and being able to model the processes in a way that's consistent with what we do see externally. But we'd like to have some direct evidence, and some direct evidence comes from helioseismology, where there are actually vibrational modes that the sun produces. So the sun is vibrating, and these acoustic vibrations have a variety of modes, kind of like taking a guitar string, plucking it in the center, you get a fundamental vibration. If you pluck it toward one end, you get multiple overtones superimposed on the string. And if you study those vibrational characteristics, you could learn more about the string or the head of a drum. You hit the drum at different locations and you set the drum vibrating in different modes. So here shown is blue and red regions corresponding to places where the gas is moving outward, it's blue shifted, or inward, away from us, red shifted. Many different modes of vibration have been observed as we look at the sun and observe Doppler shifts. This is also how, in similar ways, we study the Earth, the interior of the Earth. So that's a very useful tool. And there's another useful tool to study the sun directly, which is neutrinos. And to develop that, we need to take a look at how it is that the sun produces its energy from the deepest internal core of the sun out to the surface itself. Where does the energy come from? What is the mechanism that produces that energy? And neutrinos will turn out to play a role in the ultimate answer to that question. So how does the sun burn? Is it chemical reactions, like a fire, like a lump of coal, or some other chemical process? Good question. It could be, possibly, but here's the problem. We have, for instance, a chemical reaction, methane plus oxygen reacting to form water and carbon dioxide. That's chemistry. That's a sharing of the electrons and producing exothermic reactions and giving us heat. So possibly that's what the sun is doing. The problem is molecules are made of atoms. The sun is too hot for molecules. The molecule comes apart, but it's too hot for the atoms themselves. The atoms become ionized, making plasma. Well, if what you have to work with is plasma, you don't have chemistry. Moreover, we need about 3.9 times 10 to the 45 atoms reacting chemically per second in order to produce the prodigious power output of the sun, the incredible 3.29 times 10 to the 26 watts of luminosity, of radiation. So this many atoms are needed per second. Well, that's incomprehensible. What's 10 to the 45 atoms? It's a lot. Turns out that there are 10 to the 57 atoms that make up the sun. Well, the difference between those exponents is tremendous. But nevertheless, when you do the easy math on that, you find out that the sun would be consumed in about 8,000 years. Well, we know the sun is far older than that. So, for the fact that you don't have chemistry in the first place, even if you did, the sun would only last 8,000 years. We know we don't have chemistry. That is not how the sun produces its energy. The sun is not on fire in a conventional sense. So what's next? Once it was understood that the Earth had to be a lot older than 8,000 years, so a lump of coal could not be the explanation for the incredible power output of the sun, a new mechanism had to be found, and gravitational collapse was considered Lord Kelvin in the 1800s did the seminal work on this, establishing the potential of gravitational potential energy as it infalls toward the protosun, converting its energy to kinetic and then through frictional interaction producing heat to deliver the energy that the sun actually produces, that this mechanism could enable the sun to shine literally for about 15 million years, which was far greater than 5 to 10,000 years. So this became highly assumed to be the correct solution and was the paradigm for a long time until geologists began to understand the Earth a little better and realize that 15 million years was far short of the age that the Earth manifested. So, since the sun has got to be older than the Earth, the 15 million years didn't cut it anymore, and so a new mechanism, the correct mechanism, was still needed. So what other mechanisms are there? Well, we have something called fission. Probably all heard of fission. It's the kind of energy that's liberated in events such as an atomic bomb or nuclear power. Basically, when you split apart a large nuclei into smaller ones, you liberate energy. Now, the big nuclei are the ones that are far more likely to split apart. Things like thorium, uranium, potassium, the large nuclei into smaller ones. Well, the sun is 70% hydrogen, 28% helium, which is almost all of it. So you know what that means? It means that you can't have fission in the sun because it's almost all little nuclei that don't fission. So we still haven't gotten to the bottom of this. The opposite of fission is fusion. Fusion is the combining of light nuclei to make heavier ones. So it's really fission in reverse. At extremely high temperatures and pressures, nuclei can fuse. Generally, they don't want to. Why? Because you have things like protons. Protons coming together, the same electric charge, likes repel. So as they're coming toward each other, they repel. And that repulsion is actually very strong. If the speeds, namely the temperatures, are great enough, and the pressures are great enough, meaning they're very close to each other, then with those conditions you can get these nuclei close enough to actually enable the strong nuclear force to take over and overcome the electromagnetic force which is trying to split them apart. The conditions have to be just right. Well, the center of the sun is 15 million Kelvin and under extreme pressure. The density is about 14 times that of lead. So the nuclei are moving very fast and they're very close to each other. Perfect conditions for this to take place. They can then fuse and liberate energy, and a lot of it for that matter. We have a group of protons coming together, fusing hydrogen into helium and liberating energy. This energy-producing mechanism is so fundamental in astronomy. Let's just take a few moments to go over it in simplicity. We have two legs here that are symmetrical. They're both doing the same thing simultaneously. So let us look at one chain here. You have two protons fusing. As they fuse, they make a deuterium nucleus, which is a proton, and a neutron. Well, one of the protons had become a neutron. Did that by emitting a positron, which is a positively charged electron, which makes the one proton neutral. And it emits a neutrino. There's the mysterious neutrino. The deuterium then fuses with another proton, and in doing so, it makes a helium-3 nucleus. And a lot of energy is liberated in a gamma-ray photon. So there's a big chunk of energy, big portion of energy right there. High energy photon. Well, this has been going on this side as well. So now we have two helium-3 nuclei, and they have the ability to fuse together to make a helium-4, two protons and two neutrons, and split off 2 protons to be recycled once again. So we have 2 protons plus a third proton. On this side also, making 6 protons coming together, 2 given off, so ultimately it's 4 protons combining together to make a helium nuclei and releasing energy in the form of primarily this gamma ray photon and the neutrino, also positrons. So that's the basic proton-proton chain or hydrogen fusion in our sun. And this is going to be true as well for all the stars that we see in the sky when they burn through their normal lifetime. So how much energy is liberated in this proton-proton fusion chain reaction in the sun? The basic reaction is simply that 4 hydrogen nuclei, which are protons, yields a helium nucleus plus energy. So before we have 4 protons, then afterwards we have a helium nucleus, 2 positrons, 2 neutrinos, and 2 gamma rays. That's the overall result of this process. Well, 4 protons turn out to have a little bit more mass. There's a little bit more mass here than there is here. In fact, it's 0.7% more, 0.7%. So the mass difference is a little bit. The mass has literally disappeared. And so the energy gain that you get per reaction can be discovered using Einstein's E is equal to mc squared. So the energy has been produced by matter converting to energy directly, according to this famous expression. So when you look at the results of that small loss of mass and the corresponding energy that's gained per reaction, it turns out to be 4.3 picojoules, or 4.3 times 10 to the negative 12th joules, trillionths of a joule. That sounds like a vanishingly small amount. Nevertheless, these of course are atoms we're talking about. It turns out that this is about 10 million times more energetic than a chemical reaction at the atomic level. Therefore, it turns out the sun only needs, I say, 10 to the 38 reactions per second, which is in distinction to the chemistry where we needed 10 to the 45 reactions per second. So that's a big difference. That's a factor of 10 million. In doing this, 4 million tons of mass is converted into energy every second. Literally, 4 million tons of the sun converts into energy just to produce the luminosity that it manifests and to resist its own gravity from crushing itself in. So that translates into internal pressure. So that's the scenario that we have going in the sun, producing the energy that it needs for a very, very long time. Now, if you were listening carefully to what I just said, you should be a little concerned. Did you say 4 million tons of the sun was converted to energy every second? Yes, that's exactly what I said. Well, how can the sun still be there? It turns out that hydrogen is converted into helium at a rate far greater than 4 million tons a second, namely 600 million tons per second. So that's the rate at which hydrogen gas is converted into helium. 600 million tons. That'd be a pretty big pile of dirt, for instance, but this is gas, of course. A small mountain, perhaps. Every second, that's the rate at which helium is produced, and because of the 0.7% mass to energy transition, that translates into the 4 million tons per second of matter literally disappearing from the sun. Well, what is that? 4 million tons is the mass of a rock that would be the size of a cubic football field. A football field, if you think about looking end to end, go that wide and go that high. Walk up to that thing, solid rock. That's how much matter is literally disappearing from the sun every single second. Got that in your mind? Now that's been going on for billions of years. Every second, for billions of years, that cubic football field of mass has been disappearing from our sun, which changes the gravitational influence on the Earth, and that just seems like almost impossible. Well, remember the sun is really big, and when you do the calculation, and I have, to look at just how much of the sun would disappear, it's this little red line in comparison to the entire orb of the sun. This little red line, it's actually a little overkill, it's a little smaller than this, is literally 0.03% of the mass of the sun. 3/10 or 3/100ths of 1%. In the next 5 billion years that the sun is going to shine, that's all the mass that's going to be consumed at this rate. So 3/100ths of 1% of the mass of the sun will be gone in 5 billion years. So if that doesn't give you a little more respect for the incredible awesomeness of the sun, I find it hard-pressed to know what will. So don't be afraid, the sun is going to be there for all that time, losing mass, but negligibly. For as incredibly powerful as the sun is, it's really quite stable. It is in a condition known as hydrostatic equilibrium, which is really an important consideration to understand the processes that are taking place at the various levels of the sun. We've learned now that fusion reactions taking place in the core produce all this amazing amount of energy. Well, those gamma ray photons that are released crash into electrons and the positive nuclei. They are absorbed, and then a photon is re-radiated, and they hit another charged particle, and this crashing into charged particles, absorbing and re-radiating back out, produces a pressure that is greatest at the center and slowly diminishes as we go out as the energy of those photons diminishes through each interaction. In a like manner, gravity is trying to pull this whole thing together. So gravity is progressively having a greater influence as we go deeper and deeper into the core to precisely match the outward push of the photons trying to make their way out. So that's a balancing act between gravity and pressure, and it's unique at every layer in the entire sun. Greater and greater are those forces the deeper you go into the core. It's similar to this little picture here of these performers, and it's pretty easy to see who's under the greatest pressure. This guy in the bottom obviously is, right? Because he has all the gravitational tug of what's above, plus on his back there's pressure pushing up to keep everything in balance. So that's a good illustration of what the sun is doing. Hydrostatic equilibrium. So to summarize the basic processes going on inside the sun. At the very core, we have nuclear fusion, proton-proton fusion, producing very high energy gamma rays. These gamma rays are absorbed by the plasma, re-radiated, and make their way outward. And actually it turns out in the first approximately 7/10 of the radius of the sun, this is the mechanism that is responsible for delivering the energy out to the surface. It's known as the radiative zone. Once the energy gets to the convective zone, it's quickly transported the rest of the way out to the surface, manifested as the granules at the top of the photosphere that we already discussed, and the energy is released from the surface. The photons have an interesting life. They start as gamma rays, but as soon as they are emitted, they're quickly absorbed by a charged particle. It's a sea of plasma, and they're re-emitted in random directions. So that statistically, this process is known as the random walk. The walk of the photon through the inner portions of the sun out to the convective zone can take a myriad of paths, any of a potential infinite number of paths. And statistically, this happens so many times, and they're re-emitted, the photons are emitted in so many different directions in the process, that on the average it literally takes 170,000 years for a given gamma ray to make its way to the surface, and then 8 minutes at the speed of light to strike the surface of the Earth. So that's an incredible long time for these photons to be trapped inside the sun. When you look at the sun and feel that wonderful radiation and see the light, on the average you're looking at energy that has been produced in the core 170,000 years ago. I've mentioned how neutrinos can give us a view into the inner workings of the sun. Now, neutrinos are really amazingly elusive little particles. The solar interior is really opaque, but these neutrinos that are produced inside, if indeed hydrogen fusion is the name of the game, they can penetrate large amounts of material, light years of material, without interaction. But human beings are pretty clever, and we've devised methods of actually detecting neutrinos with special experiments way deep under the Earth to protect it from cosmic rays, other particles coming in that would give false reads. So we've learned how to detect neutrinos. Now, if fusion again is exactly what's going on inside the sun, as we just discussed, then every reaction produces a neutrino and a couple of neutrinos. And therefore, the sun should be outputting about 10 to the 38 neutrinos every second. Now, that's a lot of neutrinos. It turns out that if that's how many neutrinos are being produced at this in the sun, then the Earth should get about 1/2 of a billionth of those neutrinos penetrating the entire planet. And of those neutrinos that are impacting our great planet, about 1/1,000,000th of 1/1,000,000,000th of those are going through your fingertip every second. And the number that corresponds to is about 100 billion neutrinos through your fingertip every second, comparable to the number of neurons in your brain. So that's pretty incomprehensible. We have 100 billion neutrinos passing through our fingertip every second. You don't even think twice about it. You don't feel it. They're not interacting with you, with your fingertip. Well, the early experiments detected only about 1/3 of the amount of neutrinos needed to be consistent with the theory of fusion, production, delivering the energy that the sun is producing. So it was called the solar neutrino problem. But subsequently, the experiments and theory have gotten a little more sophisticated, and it's been realized that these electron neutrinos that are produced in the sun can actually oscillate between the other two potential flavors called muon and tau neutrinos, and they have been detected. The solar neutrino problem has been solved. We actually do have, by direct experimental evidence, the number of neutrinos that we would expect, and therefore that confirms that hydrogen fusion is the name of the game inside our sun. To finish this segment, I want to draw our attention to the visual beauty of the destructive potential of the solar wind, the eruptive prominences, the flares, the coronal mass ejections. In what is known as the Aurora Borealis, the auroral displays, which again are the manifestation of the charged particles breaking through the magnetic shield of Earth, entering into our atmosphere, interacting with the oxygen and nitrogen atoms, causing electron transitions to produce photonic or light displays that can be truly beautiful. And here we see on the planet the region based on the geometry of the magnetic field where those charged particles are spiraling into the atmosphere, so it shows the primary auroral activity regions on the planet. Here's an actual satellite image of that phenomena going on. So here is an Earth view from Alaska in this case. You can actually see tends to be circular displays of light centered around not exactly geographic North Pole, but magnetic North Pole. So here's some more views. Incredibly beautiful light displays at times. And for the next couple minutes, I'd like you to sit back and enjoy a a series of auroral displays, a tribute to the amazing power of our incredible sun.